All right. All right, class. This is where I believe this is the slide we left off on. Is that right? Just want to make sure. Okay. So we're continuing at 2.4. 2.4 is a long one just because of all the stuff, information in it. So I just want to remind you here, sample variance, it's this little piece right here. For the sample, instead of dividing by how many we have, so how many data points we have, we go with how many data points minus 1. And it always comes up, Mr. Hedgie, why? Why do we do n minus 1 instead of just n? We do n for the population, but because samples, they have error inside them, right? It's not true representative of the sample. Could be, right? But it could be some error as well. And so to compensate for that error, we do n minus 1 for the numbers to work out better. And it's very interesting in statistics. Statistics is still progressing. All right, let's go with this one here. In order to get a PhD in mathematics, what you have to do is you actually have to create new mathematics that has never been done before. That's what you got to do in any academic field. So if you get a degree in statistics, there is actually a degree, you get a PhD in statistics. You have to advance the field of statistics further than it ever has done before. And so when we look at numbers, this is kind of this whole concept of when you look at numbers, you say, hey, this number, we understand we have this concept here, right, of standard deviation. But why not do n minus 1 for sample standard deviation? Because we're going to have error. And then go through this whole process of looking at different studies. Like, yeah, actually dividing by n minus 1 gives you a lot better numbers in this. And then the formula changes. Literally, the formula changes in textbooks because of that. And so that's kind of where statistics usually ends up at. Okay, with that said, let's move on. I think we need to do another one of those. Yeah, we have some of those on the homework here. Let's go to there. I'm going to go here. So let's talk about, don't need to write this in if you don't want to. Let's talk about this whole concept of standard deviation. It means that you have a spread of your data. We good? Spread goes one way or the other way, and the middle is in the middle. So let's take a look at 3 different examples that might help us just to understand conceptually standard deviation. So here it is. I have n numbers. There's n numbers here. The average is 4. We notice, hey, this little mu guy. What are we talking about? Sample or population right here? Starts with a P, totally. We're talking population, right? That means we have all of it all together, right? We have no new numbers. Notice that all the numbers are 4. We're good? So we have 8 entries. All of them are 4. The average is 4. So the question is there any deviation whatsoever? No. So in this case, sigma is equal to 0. Good, that's what it means. All the numbers were exactly the same. Now, does that happen? Hardly ever. Okay. So now let's move on to another one here. And this is kind of a little bit conceptual. That's what we got to think about. Okay, so here it is. I have entries here. 8 is the n number again, but 4 are 3s and 4 are 5s. That's what we have here. So hold on, 4 is the middle, right? But actually to get to the data itself, we actually need to go 1 to the right and 1 to the left. So in this case, to grab the data, we're good? To grab the data, we need to spread out 1 to the right, 1 to the left. So the standard deviation is 1. We're good? Next concept. Question comes up is, Mr. Najeeb, is it all the data? No, it is not all the data. It's most of the data. That's what we want. We want to get most of the data in here. Okay, so let's do one more here. Conceptual understanding here. And I'll look to see who's writing stuff down, and if we need to write I'll wait a little bit. I totally will wait a little bit here. Okay, this one right here. Take a look at this one here. Interesting. 8 data points. That's cool. I got 2 of them having 1 as the entry, 2 of them having 3, 2 of them having 5, and 2 of them having 7. Nice spread there. Okay, and the question is this: where's the majority of the data? Well, if we think about it, if we go from 4, right? If we go from 4 to 5, I have 50% here. Is that right? We good there? 50% of the data is right there. And technically you could say that's majority, right? But what we want to do is we want a number that captures about 70% of the data. Good, 68% if you want to be a little more technical, right? Okay, 68, I'll just read off here, 68.26% if you want to be super technical. Okay, we'll get to that in just a second. Okay, so the question is, where is about 70% of the data? Well, if we go 1 away, we capture 50%, but then we have to go all the way 3 away to capture. But when we get to 3, we're capturing 100% of the data. We're good? But there's actually now, there's spread with the 3 and the 5 too, right? So once I get to plus or minus 1, I already have some of the data, right? So now the question is, if I go at 3, I get 100% of the data. So the standard deviation only wants about 70%, 68%. So in this case, the spread is not going to go all the way up to 7. It's going to be roughly about 2. I mean, this one it's calculated 2.2. So if I go out to 6, if there's more data points inside here, we're good. It's not just kind of, but if there's more data points, if I were to go out to about plus 2 on this side, minus 2 on this side, I would have captured about 70% of the data. Does that make sense to you guys? Especially if there was more data in here. Okay, so then we do this. We have some writing for you guys. So what does standard deviation mean? Here's what it means. That for our data, about 68% of the data is going to lie within 1 standard deviation away. Now notice it says about, right? It's not precise. Is it going to work all the time like that? No, but depends on how many data points we have. All right, if you go 2 standard deviations away, then what you're going to have is you're going to have roughly about 95% of the data within those 2 standard deviations. And that's pretty cool. At that point, you say to yourself, look, do I have like most of the data in here? Absolutely. Once you hit that 2 standard deviations, very important in statistics. Once you hit 2% or 2 standard deviations away, you're almost confident you have most of the data in here. All right, if you want to go super, super precise, if you go 3 standard deviations away, and you work with 3 standard deviations, at this point, you've gathered yourself together 99.7% of the data. And that is super confident. Look, I am working with almost all of it. 0.3% is not that significant of me not including that data in there. We're good. And we're also going to use it to compare standard deviations between other things too. So that's chapter 6 when we actually get into that. Okay. I see almost everybody's done writing. Thank you so much for that. This one is actually inside your textbook, so I don't want you to write this one down, but the next one here. So this is what happens here. What happens is that we want to have this right here. It's called, hey, this is symmetric, isn't it? Nicely symmetric. Notice that the middle is going to be like right here, right? So if I were just to divide out the data, we like data to look like this. This is a nice curve right here. And so if we go one standard deviation away, here's our 68%. So 34% goes towards the left side, 34% goes towards the right side. That's how we've encapsulated the 68%. Good. Let's see. I don't think anybody has a textbook here. Let me look up the page number so you're not drawing it out. If there's no need. The next one I want you to draw out, not this one. Now, I'm not sure why the book does not have the more precise view of it here. Okay, you guys can all just write down. I'm gonna give you the page number real quick here. And it is on page 88. So on page 88, just gonna have that as a reference. Oh, it does do that. Okay. Then, since it is 95%, we might as well break up that extra percent, right? Because we want 94, and then that percent goes on one side, percent goes on the other. So to have 95% of the data, that means you have an extra 13.5% here, which is in between standard 1 and standard 2, or standard deviation 1 and 2, going towards the left. And then to capture the rest of it, we have that right there. Are we good? Okay, but to be more precise, and the precise one. So this is more like general numbers. We're good? If that makes sense. Is it used? Yes, absolutely. It's used on like manufacturing where maybe precision is not needed. Psychology where precision is not needed, where it's maybe like a rough study of something, not like we just need to get the exact numbers. Okay, and then if we actually dig down to the decimal place for it here. So it's more like this. And let me just check if that's this one. Yes, this is inside your text. This is page 88 again. So notice it's more precise now, right? It's actually 34.13. So now we're going out 2 decimal places each time, just to make sure we get all that information here. And let me just check something real quickly here. I want to go, let's do that. Let's do about, yeah, it says about. Can you guys do this for me here? Let's see, this would be, let's see, points. Yeah, I could add them in here. 34 plus, that'd be 26. Is that true? Nah, hold on real quick here. I'm gonna go like this here. This one, I thought the first one was inside your textbook. No, it's actually this one inside your textbook here. So we're good. I wanted a more precise definition. This is on page 88. Now we're good. Okay, that's the one, because we're gonna go on to an example. So let's jam with this one here. So a survey conducted at the National Center for Health. We have sample of the average height of women in the United States, ages 20 to 29 was 64.2 inches. Standard deviation of 2.8. So you guys tell me, estimate the percent of women whose heights are between 48.5 and 64.2 inches. So I think it has to do something with the standard deviation. What do you guys say? If you're at 64.2, how many standard deviations do you go down, looks like, in order to get to 48.4? Or or 58.4. I don't know, all yours. So how many 2.9s does it take to get to 58.4? Got some answers. Tell me if you guys agree with 2. True, 2 is true. So just try it. Kind of go 64.2, subtract 2.9. See where you're at. Let's subtract another 2.9. See if it gets us where we need to be. So I'm thinking 64.2, subtract 2.9. What is that number? Sorry, 61.3. Perfect. Okay, not there yet. So another 2.9 away. Awesome. I get what I want, which is 50. So let's see if we can draw out this diagram here real quick here. So I have this. I have that. I'm at 64.2 right here. Everybody agreed there? And looks like I'm going down 1 and I'm going down 2 to get me to 58.4. So my question is, how many, if the height of women is symmetrical across the US, right? And then we do a little interesting thing to get it symmetrical here. So the question is, what percent of women are we talking about at this point? So again, 47.5, that's cool. Let me go back to here. So if this is 64.2, this is 58.5, perfect. How about we add these guys together? We good? Because those are the things we're talking about. We're talking from the middle down this way. And we stop. Okay, and what do you guys say? Perfect, I'll go with that. 47.72%. Roughly a little under half the women here. Okay, are we good? So that's how it's called a normal curve. That's how the normal curve works. The rest of statistics, when we do this stuff, we're going to be talking about that normal curve for the rest of practically the rest of the time. Okay, huge in chapter 6. All right, so as soon as we finish chapter 2, again, we are going to jump into probability, right? Which is a totally different topic. You could almost say it's a totally different class. How we deal with things possibly happening. We good? That's what we're looking at. Okay, so there it is, normal curve. We're going to get it way into it a little bit later on. But let's handle one more thing here. Chebychev's theorem. How about that? Good older fella, born in 1821. Whew, that's crazy. Died in 1894, age of 73. And he contributed a lot of things to probability, stats, mechanics, and number theory. So he had this little theory that we still apply in stats. Has to do with the normal curve. And what he said was this, the quick little formula. Instead of looking back to the chart and trying to figure out, oh, 34.13%, oh, 13.59%. He just said, look, the formula, if you want to, portion of data lying within K standard deviation, no matter which kind of curve it is even. It doesn't matter what kind of curve. It could be symmetric, non-symmetric, whatever. But there's such an easy formula. It's just 1 minus 1 over K squared. And K is the standard deviations away. And such a quick formula. And that's, I think, how it's presented here. But it gets to the deviation stuff right away. So if k is equal to 2 of any given data, we plug in the 2, 1 minus 1 over k squared, put the 2 in there, makes 1/4. 1 minus 1/4 makes 3/4. So 75% of the data is going to lie within 2 standard deviations away. Now, the chart that we saw, that was the very, very precise piece, right? This is a very loose definition. 3 standard deviations away, no matter what kind of data set it is, as long as it includes a lot of numbers, you're going to get almost 90% of the data within 3 standard deviations away. So let's look at his. Okay, I don't want you to write down the bottom stuff, just the top highlighted and then the formula itself. I like it, quick formula, and the question is, it doesn't matter if it's symmetric, non-symmetric, you'll get that data. Okay, let's just do one example real quickly here. This is, and sometimes, I will say this, sometimes things are not the same, like the average height of women in a population, or men for that matter, right, or United States. You know, it's going to be low on one side, right? And then low on the other, it's going to bunch up in the middle, right? So let me go back real quick because the people that just came in. So we were looking at something like this right here. This is called the normal curve. I didn't want to do that. Here's something called the normal curve. It goes up, comes down. And we said that about 68% of the data is going to fall in within 1 deviation away, to both to the right and to the left. 95% of data is going to fall within 2 standard deviations away. And at that point, you have like some confidence that like, man, that's the majority of it. Once you go 3 standard deviations away, talk about being very precise. 99.7% of the data you have, yes, I have a majority of the data, right? There's a more definiteness there. But some things do not fall into this nice curve. Sometimes the things look like this. It's the age distribution for Georgia and Iowa as shown. So this does not look like, right? You're not going to have less children, right? And then all of a sudden, at age 25, there's a whole bunch of 25-year-olds, right? And then it comes down again, right? That does not make sense. So this is the number, the age of children in years. And obviously, it's going to just taper off at the end only, right? So it's a one, sometimes we even call it a one tail. Okay, so let's see if we can figure this out here. So apply, I think it's Chebychev's. I think that's the way I heard it pronounced. Chebychev's theorem for Georgia. Let's go to Georgia here. Boom. And we're going to use 2. So we want to go 2 standard deviations away from the middle. So the middle looks like in Georgia, the average age of a person in Georgia is 37.3, and that's so cool. Look at that. It's a mu. That means they took it from some kind of data, most likely census data or something like that. They somehow got the population. So 37.3. I got 22.2 as a standard deviation. Now the question is this: using theorem, using k is equal to 2. So we want to capture 75% of the data. We good? And then also notice this real quick here. We should point this out. So 37 it's pretty close to 35, true? Like, okay, give or take, right? So if you go 35 to 0, right, that spread right here is it takes you all the way down to 0, right? 35 going that way. But if you go 35 this way, you still have some people over here, right? You still have 70 of you right there. You still have more information on the one end where you don't have it on the other, right? So let's talk about that as well. This is an example that does all that. Okay, let's jam. So here it is. If I say k is equal to 2, so that means I'm looking for 75% of the data. And here's another formula here. It's mu minus 2 times sigma. So we want to get 75% of the data here. Okay, so let's see what it's doing. It's 37.3 is here, minus 2 standard deviations away. And standard deviations is 22.3. Everybody good there? When you do that in the calculator, you wind up with a negative 7.3. What does that mean? So to capture 75% of the data going this way, right? And this way, I need to go down about 44 years down. But I'm past the 0 marker. So in this case, I'm going to capture all the rest of the data with all the infants. We're good? It would not make sense to go down to a negative. So this case, we're just going to use 0 since age can't be negative. Let's go the other way. Can you guys add this one now? So the average 37.3. Can you guys add and give me that number? What is that number when you add 2 standard deviations up? Yes. Perfecto. Yep. Going the other way, adding instead of subtracting, goes to 81.9. So now what did we say? According to Chebychev's theorem, 75% of the population in Georgia are between 0 and 81.9 years old. And that's going to capture, let's see, about 75, right? 75% of the people. And so what do we do? 2 standard deviations for the most part is important to us because anything outside of those, we call that unusual. And so a person that is age 100, because they're more than 2 standard deviations away, we say that's unusual. Unusual data point. Okay, one more. Let's go. Yeah, let's go back because we entered. So it's this little piece right here. So when Chebychev initially looked at it, he said instead of being a normal curve, goes up and then comes back down. Any kind of curve whatsoever, as long as there's enough data points on there. You know, it can't be like 5 people, right? But the state of Georgia, that's a lot of people, right? There's enough data points there. So he said, look, within any kind of data set, going up high, going up low, if this little easy, nice, easy equation gives us this whole concept of, if you plug in the 2 into here, any data point, as long as you're 2 deviations away, is going to have at least 75% of the data in there. Could have more, but you're going to have at least 75 with enough data points sitting. If you have 3 standard deviations, that means you're looking at 88.9%, which is, that's his theorem, right? Which means any kind of curve whatsoever, going up high, going low, sometimes having two hills on it instead of one, who cares, right? You are going to have that much data. What we normally do in statistics is this little piece right here, though. That's what we normally do. It's a normal curve, it goes up and comes down. So notice 2 standard deviations away is already going to give you 68% on a normal curve. Sorry, 1 standard deviation. 2 standard deviations will give you 95%, right? But Chebychev, what he was trying to figure out is, no matter what kind of data, especially data that does not do this right here, it's going to be way off because you have more data on this side maybe, right? So age is a perfect example. Age will never be like this. You're never going to have a small amount of infants, a lot of people in the middle, 25-year-olds, 36-7-year-olds, and then all of a sudden it tapers off. You're going to have it going up very high and then slowly going lower. And so, does that make sense? So it applies to this perfectly, yeah. So you're going to have a lot of infants, you're going to have a lot of kids, and eventually you're going to start dying off. Will never resemble a normal curve. But Chebychev's formula is still going to work here. So we do that one. Does that make sense? Sort of, okay. Cool. Yeah, that's right. And also, I guys encourage you guys, let's take an honesty question here. How many of you guys opened up the book and looked at the rest of 2.4, just kind of perused it, looked at the examples, and then also open up 2.5, take a look at that stuff before coming to class today? Gotcha. Okay. Maybe it would be a good thing to do. Go. Okay. Okay. Gotcha. Just helps a lot. Helps a lot because what you do is you allow your brain to process something before coming and sort of seeing a full-blown lecture for it. Super good technique for any class whatsoever, right? History class, right? You're gonna like, hey, I'm gonna talk about the Civil War or something, right? Okay, let me just kind of thumb through. What is it? Or like those bold text, right? Like causes of Civil War, right? Major battles of Civil War, reason for the end of the Civil War. Perfect. Now you got a schema of what the lecture is probably going to be about, right? Like, hey, causes, we're going to take a look at major battles, and eventually we're going to see how things ended up. You just built a schema, right? Even before coming to class, but your brain is sort of prepared to receive it in that way. So super duper good way to do stuff. Cool. Okay, let's jump to one more item. Let's see, two more items before we get out of 2.4. So this one, another formula for you guys. Sorry, throwing formulas at you. This is called the sample standard deviation for a frequency distribution. Whew, man. Sorry, guys. Going all the way back to 2.1. Going back to 2.1. Remember we had frequency distributions, right? Remember we looked at the midpoint of a class, right? We looked at class limits. I'm just trying to refresh your brain. We looked at class boundaries, I think, right? And then we graphed them. So now the question is, how do we look at standard deviation if you have a whole bunch of grouped data here? And we'll do this one together. But eventually, what we want is, we want to add up all the x minus x bar squared. So this is the sum of squares, right? But we also want to multiply it by the frequency. Once we do that, we divide by n minus 1, because remember it's a sample, not a population. And we take the square root of it. Okay, not going to do all at once. We're going to do it step by step to get us to there. Week from today. Second. A week from today. We'll come back on Thursday. We'll do any other homework questions you guys may have. Okay, guys, let's do this here step by step. Let's go with, I just want to do an easy one here. And we have one, yeah, that's right. We have to do one with midpoints inside it too. Okay, we have 2 examples off of this. So here it is, random collection or sample of number of children in a household. So this is just taken from a certain region. This is fake data because there's no parentheses with little blue stuff next to it, right? So there's number of children in 50 households. We've got 1, 1, or 1, 3, 1, 1, 1, 1, 2, 2, 1, 0. All the good stuff here. Don't copy down the numbers themselves. Okay, don't do that. We'll start a distribution table in just a bit here with that. All right, let's go with it here. So all those numbers here. And I'll give you the frequency for them just so we can get going faster here. So normally what you do is you make a frequency table and then you start, oh, we did tally marks. Remember doing those tally marks that we did when we did the first time on this stuff? Okay, so we have this. Let me give you frequencies right away. So there were in the data set just now, there were 10 zeros. There were 19 ones. So 2, 7 twos. So yeah, we're gonna write, yeah, so we can start writing this out. All right, 2 4s, 1 5, and 4 6. What we want to do for a sum of squares, because that's eventually where we want to go to, right? And notice on the top, you always have the formulas for it. So let you work a little bit here as we go through it here. So, yeah, you probably need your calculators out as we do this, do a whole bunch of calculations here. First things first, we're just trying to find the mean. We're trying to find the average here. Do you guys remember average of group data? Now it's 2.3. I want to know the X bar. That's what I want to know. For group data, we just multiply this times this first, right? Instead of adding it, you could do that, right? You could say, let's see, 0 plus 0 plus 0 plus 0 plus 0 plus 0 10 times, right? Then you could say 1 plus 1 plus 1 plus 1 plus 1 19 times. Then when you're done with that, no, too long, right? I don't want to do that. So how about we just multiply across? 0 times 10, 0. 1 times 19, 19. Yep, 2 times 7. Thank you. 3 times 7. Perfect. 4 times 2. Love it. 5 times 1. 6 times 4 would be 24. Okay, now can you add that up? So this is just to get us our mean of our data set. That's what we want to do. Okay, anybody give me a total here? We're just trying to average. Yeah, we're trying to average right now. What's the average? 91 is the total. Okay, boom. There it is. Yep, 91 is total. Yep, and we had 50 data points because it was 50 households. That's true. We could also add up our frequency table just to make sure that we added them up correctly, right? Now we didn't miss any. All right, guys, let's see. 91 divided by 50. I think that's where we're at. All right, and then the question is, how many decimal places do you go? Is it 2? Is it 1? And so that's the problem here, is that like which decimal place are you going to use? In this case, let's go with 2 decimal places. So we're going to use 1.82 as our average for our sample stuff. Cool, cool. All right, let's do this here then. Now I got that. Now I can do my next column. Anybody tell me what's the next column going to be about? What do we do for the next column? Think back to 2.1. For the next column, what we do is we figure out how much spread we have, right, from the middle, right? So the next one would just be, you got this x value, I'm going to subtract off 1 minus 82. So tell me you guys are done. I got 2 more people writing stuff down, so tell me if you guys are done. So 1.82, right? That's cool. So the next table is going to look like this. And this column here, I didn't copy and paste this column for some reason. So this column should be the next one. So it's just going to be the next column that you have. We're good. Just bring it over. So if you want to label the top column as x minus x bar, next one will be x minus x bar squared. And then it'll be x minus x bar times the frequency. That's the one we're going to add. You guys remember when we were, last time we just added this column only, right? To get the standard deviation. Remember that? Just from data itself. So we're going to multiply times f. Okay, let's go with it here. See, let me do the first one here. 0 minus 1.82 gives you a negative 1.82. Okay, 1 minus 1.82, which should give us a negative 0.82, and you'll see a little pattern happening. 2 minus 1.82, and what would that be? It's a tricky question, absolutely. 2 minus 1.82, punch in the calculator, see what we get. Point 18 is fine by me. Okay, the rest of it, you guys should see the pattern here. So notice we're just going up by 1 each time. So 2 minus 1.82 is 1.18. 3 minus 1.82 is going to be 1.18. Anybody some guesses for the next one? Uh-huh. And without a calculator, what's the next one? Absolutely, because you're going up by ones each time. You're at 4.18. Okay, cool. The next column, you probably do need a calculator here. So can you go, remember we talked about this last time, just real quick. If you're going to use the negative, you got to put a parentheses in. We're good? Or, you know, if you have a negative times a negative is going to be positive. So who cares about putting in the negative originally? So in your calculator, just put 1.82 to the second power and see what we get there. What is the answer there? 3. Yeah, and in this case, we have 2 decimal place accuracy here. When we do this here, we want more accuracy at this point. So we're going to put 4 decimal places out. We're good? So 0.82 squared. Perfect. Awesome. Thank you guys so much. Thank you guys with calculators helping us out here. 0.18 squared. Perfect. Okay. I'm going to give the rest of the answers so we don't have to wait or you guys have to call us because I already figured out myself. So there's the rest of the answers. Again, you're just squaring it. Okay. Something we did not do before. because we didn't do group data before, right? We just did straight data. Is we got to take this frequency right over here, this little 10 right there. And we're going to multiply 10 times this right here to give us the number right over here. Again, instead of having 50 data points going down our side, right? What we did is we just condensed it down to 7. Okay, so I'll do the first one, the difficult one here. 10 times 3.3124 makes 33.124. Give you guys 20 seconds. Try the next, maybe the next 2 or 3, just to get the same answers, and then I'll give you guys the rest of the answers. All right, let's see, 0.6724 times 19. Anybody with that one? So 19 times 0.6724. So perfect. Okay, cool. Okay, now that you guys have done it a little bit here, let me give you the rest of the answers, and you guys just check to make sure that's the same answer as yours. And once you do that, can you guys add them all up just real quick here? I know it's number crunching. I understand. Just want you guys to number crunch a little bit here. Mr. Geov, seriously? I will say some people, what they do is they teach this class solely by calculator, meaning like, here's a function the calculator does this, here's a function the calculator does this, here's what you do. Because there's a way to calculate standard deviation this way. There's a standard deviation button on the calculator. But this kind of gives you the inner workings of it. This is why it works out this way. I think that's a better way to teach the class. Okay, tell me when you guys done calculating it and summing it. Tell me the answer. What you guys get? Perfect. I got 145.38. Totally agree. All right, waiting for the others to get that as well. Just to confirm. All right, we're good. And then if you guys can use the previous formula that we just have in our notes, right? About the sample standard deviation of group data. Can you plug that into the formula now and calculate the standard deviation? So it should be in your notes already. All right, those that forgot it real quick here. Let me go back to it real quick here. So show all slides. I think it was this formula right here. Right, it was this one right here. Right, you can calculate that. And if you get a number just slightly under 2, I think you did it correctly. So you plug that in. Because it's a sample standard deviation, notice it's n-1, right? N-1 is your divisor. A little bit low, just a little bit low for some reason. You divided by 49 or 50. All right, again, because this is a sample standard deviation, right? We're going to divide by 49. Are we good there? It's the 50 data points minus 1. So let's go back to our data. I don't want to take too much time, and I want to know where you guys are at here, but it goes here, and it goes to here. 145.38 divided by 49, then take the square root of it. Roughly 1.7. Okay, you guys talk to me here. Punch in the calculator. Is that what you guys got already? Hopefully. Nope, no one's talking to me. Gotcha.
That's the number that yeah, yeah, that's what we got. So then replace the formula. We use 50 points, and in the formula it's pretty much 50 minus 1. So minus it because it's a number of inches. Yeah, minus 1. So 54 inches. Yeah, and we just minus that. Yeah.
Okay, talk to me. Did everybody get 1.7 that had a calculator that tried? Are we good there? So we got one more type of group data. So this one is when we actually have individual points, right? But remember when we had actually classes? Remember that? When we had and a midpoint in the class here. So this group data, just to give us the clarity of differences here, this group data had X values, and those X values were from the data itself. You guys remember the out-of-pocket medical expenses? Remember that one? Where people spent between 100 and like 155 to 190, right? We had that little range there. Good, Edwin. Uh-huh. Square root.
Square root first.
Uh-huh, yeah.
Or something else. Like, all the way up. 0.172 something else. Would it be the same outcome every time?
No, that should be the same outcome. The only, let me just take a look at your calculator real quick here, because that's what we are here for. Let me see what your input value.
So the formula itself is you have to divide first and then take the square root, because the n-1 is underneath the square root.
Does that make sense? Yeah, let me go back to it real quickly here. Just clearing up some stuff right here. So notice the square root, the formula is all the way down here, right? And encapsulates the n-1. So you got to go from the inside to work outside. From the inside, 145.38 divided by 49 first, and then square root that piece. We're good? You want to try it yourself just to make sure you got it? Please do. That's why you guys are here. So you guys can try it, test it, experiment on it. This is about being in school here. And tell me you're good or not, or need more clarification, no problem. Cool. Okay. All right, so group data, let's talk about this here. So one kind of group data is that you have individual points right here. That's one type of group data right there. The other type of group data is when you have a range like this, 0 to 90. And now we have classes that we've built. We good? So let me see real quick here. I'll go back where it came from first here. It came from this. It says a figure shows the result of a survey of 1,000 adults who were asked how much they spend in preparation for personal travel each year. So before you go out on your camping trip for the summer, question is, what do you use it and what do you use it on? So make a frequency data, use the table to estimate the sample mean and the sample standard deviation of the data. Oh, this one's actually real stuff. Look at this, adapted from the Travel Industry Association of America. I wonder what year it is. But there it is. So let's talk about the data. The least amount, less than $100. That's funny. They try to put in a car wheel because technically you can make a pie chart out of a car wheel. Haha, that's fun. 380 of them said less than $100. That's it. 230 said between 100 and 200, and then we go on so forth. And some people spent under or over $500. $70. Okay, so then we're going to take each of these, put them into classes. Here it is. Your classes are 0 to $99, 100 to 119. Now we don't need to do class boundaries here. There's not the whole exercise here. We're just trying to figure out how to get to a standard deviation, sample standard deviation. Well, first things first, we have to get to the mean first, right? Because we're going to do the same process that we did before. So in this case, really the only difference is you have to find the midpoint of the data. Are we good? That's it. Just find the midpoint of the data and the rest of it's going to work the same. And so finding the average, finding the mean is a little bit different this time because of that. So what is the what's the middle? What's the midpoint of 0 and 99? I don't know. I figure this. You take 0 and then you add 99 to it and you divide by 2. Are we okay with 49.9, 49.5? Okay. Sorry, you guys tell me if you need for me to wait for you guys to sort of build the table off first here. I made these as two different tables because one is actually just to get the mean first, and then the second part is to get the standard deviation, but you can keep on adding columns to this. It's no problem. All right. Once we found the first one, you guys talk to me. How do you guys find the second one? There's two different ways. Go for it. Yeah, absolutely. There's the two different ways. So you can do the same thing that you did for the first one. Take 100 plus 199 total, divide by 2, and gets you 149.5. Or you look at the class limits, right? The class limits are 100 each time, right? There's a difference of 100 each time, and it has to be the same way, right? So let's add 100 each time here. That should be the average, or the average here. We got ourselves a problem. Guys, this is it, the data problem. Welcome. We have 70 people that said they spent over $500. So is that $500 to $599? Is there one person that spent like $12,000 for repair on their car? Was it the motorhome that like seriously needed repair? And so they re-gutted the whole thing and they spent 12 grand? What's the average of 500 plus? Not cool, huh? Yeah, like how do you even find that out, right? Do you go back to the 70 people like, hey, what did you spend? Let me give the average. Okay, so what we do is we just keep the same flow of information down. Now, is there some turbulence there? Is there some sampling error? Yeah, at this point there is, right? Because of that one. If you have enough data points in there, could you have better answer, better numbers? Yeah, you could, right? If you asked, if you asked 500,000 people, right, how much it was. Right? If you expanded your class data a little further down, right, that would have been good too, right? Maybe did a few more until you're like, there's only one person that spent over $800, right? So that's kind of where you get the class structure from. Okay, but in this case, what we do is we just keep the same thing down. Frequency. So we get frequency is given from the other table. I'll give it to you, 380. We looked at that, 230, 210, 50, 60, 70. And that was from the previous table. I'm going to add up my frequencies to make sure I get the same number that I got from, that was part of my study, right? This is a check. This is a check summation right here. If I add this up, I better get 1,000 because I asked 1,000 people. And if I don't get 1,000, that means I'm missing some. It's like when you do your budget, and like you're just missing those 20 cents. Like, where's those 20 cents come from, right? Or it was that darn penny. Same thing here. Yep. I added up the frequencies. So I want to know how many times, right? Or how many people are in the first category. And so I asked 1,000 adults. So when I add this up, I better get 1,000 here. This better match the number of people I asked in my survey. Yep, it is a check of my data. Okay, my next one is now trying to get to the mean here. So here we go. So I'm going to go with a midpoint from the classes, right? Because I'm not going to go and ask those 1,000 people again, but oh, sorry, let me do this here. Let me ask you, like, how much did you actually spend, right? They may not even know. That's the problem, right? They don't know if it's $120.58. I was like, about 150. Right, so that's about as good an answer as you're going to get. So we use the midpoint to kind of give us that little middle ground of that section, assuming that if you have enough data points, you're probably going to get that little middle there. So 49.5 times 380, I'll give you the numbers here. It should be 18,810. All right. And let's do this here. Just a 1, 2, 3, 4, 5, 6. Sarah, can you tabulate the next one? Jocelyn, can you tabulate 249.5 times 210? We'll do that. In the back, 349.5 times 50. Surreal. The next one down. And Edwin, the next one down, the lower one right here. Just so we get some numbers here. Sarah, back to you. I'm good with that. 34,385. Jocelyn. 395. Perfect. Sweet. Awesome. Surreal.
26,970.
Awesome. And Edwin. Perfect. And I will tabulate the answer. There it is. 192,000 is what I got. Okay, so this is for the mean. This is for the average, right? What notation are we going to use? Are we going to use mu or are we going to use X bar? This is a survey, huh? Did we ask all the adults in America? No, we only asked 1,000. So in this case, X bar would be the summation of X's and the F's multiplied together over 1,000. And we have 192. There it is. The sample mean of this is the $192. So you could say on average, at least in our study, on average, people spend about $200 or $192 to prep for a trip. At least their maintenance on their car and stuff. All right, how about you guys? Does that sound about right? I'm thinking what, changing the oil, right? That's like $60, right? Maybe I'm thinking probably the tires are probably gonna cost the most, right? That's, I think, the distinction. Which one? 380. Oh, this one right here? Oh yeah, sure, Justin, absolutely. Here, let's go back. It was this 380 that was right here. It was just the numbers that were given. Okay, everybody okay with 192? We're not done yet. That we just got the average down. So can you guys can you subtract 192 from each of the X's? That's what we want next. And so tell me if you need to go back, okay? I'm gonna go back to that. I'm gonna go forward. So here it is. I want X minus X. Hey, there should be X bar over here. I'll do the first one. You guys confirm the first one. This would be 4950. 4950 subtract 192.50. All right, and with the calculator, let's do this here. With the calculator, can you guys just calculate the next one? And I'll give you guys the other numbers, just so we don't waste time calculating. So what would be the next number? Everybody tried on their calculator. So let's go back to what we need. We need, this would be 149. There you go, 149 minus 192. 149 minus 192 is what I got. Anybody with an answer? Say again. Negative 42.5. Perfecto. Okay, let me guys give the rest of the answers. I just want to make sure you guys did it. And also, since it goes up by 100, or by 50s, let's see, by 50s, by 50s, 100. Okay, let me give you guys numbers as well, okay? The next set is just each of these numbers, 142.5, and we're gonna square it. These are gonna be kind of big numbers here because we're squaring a hundreds place. So 20,306.25. Just big numbers here. If you wanna try some of them on the calculator, go for it. But here's what I got. And still we're not done. Uh-huh. Let's go back to the previous slide. That's why we have it on your notes. The frequency, boom, the 380, the 230, the 210. So then you got to go back to this one to get wrapped. I just can't fit all in one slide here. So multiply with frequency, which is 380 times this. Again, big numbers, guys. Okay, and you guys make sure you guys know where those are coming from. We're good. That's the frequency. That's the 380, 280, or 230, I think, right? Then the 210 is the next one. Okay, grand total. 25,668,750. Sorry, guys. Again, lots of number crunching, but at the same time, I think it gives you an idea of what's sort of on the back end, all the stuff on the back end of this. When you guys get to graduate school, they usually will have some kind of software there. StatCrunch, Minitab, even Excel. Most people are kind of, you just do Excel because Excel's free. Excel does have this. They have all these tools inside them. So you actually just put in the data. As long as you have the data correct and everything's fine, you click sample standard deviation, click, and it does. That's what it's crunching. It's crunching all this stuff on the back end. And it'll say, dunk, sigma is this. I'm like, okay, now I can move on from there. So computers opened up a huge amount. Even Excel, by them pushing all the statistical programs inside there, opened up a lot more usage for stats. And then usually Minitab and StatCrunch, they're used in specific areas that have everything sort of dialed in for that area. Whether it's manufacturing, nursing, medicine. Cool. All right, final things here we go. So here's our formula. Whoa, sorry, there should not be an extra square root here. That does not belong there. It should just be, let me erase that out of there. What the heck? Okay, so there's our conclusion to all the stuff we added here. And then 1,000 adults were asked, but because it's a sample, we're going to go with 999 as our divisor. So do the fraction first. After you do the fraction, then you take the square root. So 164, oh, sorry, 100. So 192 is the average. 160 is the standard deviation. Right, then we have this whole concept of, right, where's normal or the most of the people spend between this and this. Do you include that as one standard deviation? Or do you include it as two standard deviations, right? But anyways, 160.3 is what we come to. Okay, so now the only thing is with our mind, we could say like 192, that's great, and 160.3, that's great. But we like to think of percentages, don't we? More like, hey, I have this much percent of this, how much this percent says. So we do function in percents. And so one thing with standard deviation is this whole concept of coefficient of variation. It's a number that really describes how much percentage you have. And so the formula for it, for the population, again, here it is, population data, sample data. In this case, there's no difference in the formula. There's more of a difference in notation, right? Because the Greek letters are standing for population. English letters are at least X with a bar on top of it, and S stand for the sample data set. Since we're getting into a lot of formulas here, I think we should kind of take a look at your book. If you go all the way to the back of your book, and you got this flap that's kind of at the end, flap that just keeps on opening up further and further and further. And so starting with chapter 2, notice right here, it's just a list of all the formulas that we have in that chapter. That's a pretty cool thing. I'm glad the book did it. So chapter 2 formulas, right? And then it just goes on. Chapter 3 formulas, chapter 4, 5, 6, 7, 8, 9, and 10. I thought that's very, very useful sort of idea. So this little flap that opens up. So you have one page that has all the formulas. And you're good to go. So we're still going to use a table out of this too sometimes, at least the flap. So that formula should be there. I'm going to actually check if it's there as you guys are still writing it down. Yeah, chapter 2, a lot of stuff here. There's the class width, the midpoint, relative frequency, the means, the distributions. And as I'm seeing this here, standard deviation, coefficient of variation. Interesting. Coefficient of variation is not on here. I mean, it's like a slight minor thing, but so if you want to prep for the exam a certain way, that's the way we do it. Okay, real quick, let's go for it. So we have to do this here. Tell me if you're good, because I see a few people still writing. All right, good. Let's go with it here. So I got this here. Let's see which one we're going to use. I think I'm going to give you the data for it though. So table shows the population heights in inches and weights in pounds of members of a basketball team. So this is all of them. I think, yeah, this is all of the whole team. So how many people on the team? 12. Okay, that's cool. So here it is. Find the coefficient of variation for the heights and the weights, and then compare the results. So I'm going to number crunch for you. We're not going to do what we did last time. Make tables, not cool. So here it is. I'm going to give it to you. So the average, if I took the average height, it would be 72.8 inches. if I tabulated all that stuff, it'd give me a standard deviation of 3.3. Give me the coefficient of variation for the heights. So can you plug in the formula that we just did? Population formula or sample formula? Which one? Starts with the P. Population, because we're just looking at one basketball team. We're only interested in that team. We're not interested in the heights of all the teams in the US. So there it is. The height would be sigma over mu times 100. So go for it. Can you guys plug in the formula there real quick? Boom, boom. And give me the number when you have it. So this is a percent now. Oh, cool. Okay, got some person with the answer already here. We're good? Something like that. So 3 on 3 goes on top. Standard deviation divided by the average, which is 72.8. Multiplied by that gives you 4.5. Let me just check something. Okay. Oh yeah, and the weight. Okay. Okay, now let's do weight real quick here. Do the weight because we're just trying to figure out height and weight, right? Weight is again still mu. CV of weight, or you can just put CV and W, small little W there, so you know it's the difference here. So can you guys give me that percent right here? Go ahead.
How do I know whether to go with sample or population data?
Depends. Quick question comes up is how do you know I use the sample formula or the population formula? You have to go back and find out what's the study talking about, and I'll give it to you here. So this one just says table shows population. That kind of gives it away. Heights and weights in members of a basketball team. If it was a sample, it would be like this. It's a
So we give us S and X.
yeah, but as far as the yeah.
Like, so if I were to put a sample thing, it would say, it would like pull up from the basketball team, right?
Yeah, that's true. Yeah. So another way to do it is a sample of, or 20 people were asked, or from a sample from a football team, basketball team of 20 people, 10 people had their weights reported. Then you know, like, okay, that's a sample. Or to figure out the weight distribution of college basketball teams, right? The West Hills College basketball team was selected, right? Now you know, like, hey, there's something out there bigger, but I'm only using this data here. That's kind of what you should sort of see it as the verbiage. There'll be a little more verbiage there. Good question, though. Very good question. Okay, boom. So anybody got this one? Give me a percent. 9.4, boom, okay. So now let's compare these two. I got 4.5 for the first one. I got 9.4 for the second one. And the question is, what does all this mean? Well, it means variation. It's how much variation do you have from the mean? And so we say it like this, if you guys want to write it down here. This is kind of the English way of saying it. It says the weights, which is 9.4%, are more variable. And that's kind of what we're looking for. We're looking for that little guy right there, more variable than the heights. So there is more variation in weight. You think height might be it because, you know, you have the guards, which are much smaller, right? And you have the center much larger, right? So that changed there, right? Versus how much people weigh on the team. Does the guy weigh 150 and the other guy weighs almost 300 pounds, right? You have that sort of distinction. So which one carries more variation in the basketball team? That particular basketball team? It's weight. There's more variation in the weight than in the heights. Heights are more closer together than weight. Okay, let's, are we good there? We done writing stuff out as well? Boom. Okay. We are done with 2.4 and I am thinking, let's jump to 2.5 for a little bit here. Let's get as much as we can and then we'll come back on Thursday. We can finish it up, at least have a sense of what we're trying to do here. Okay, let's go. Yeah, let's go like 10 minutes-ish here. See how far we get in 10 minutes. I got 1, 2, how many slides here? Okay, 24 slides. Let's see if we can get up to maybe like 12 on the slides. That way it'll be close.
Consistent chapter.
1 and 2. Yeah, we went over the study guides earlier. I'll go over the study guides with you guys afterwards. Okay, guys, let's go. 2.4 measures of position. Now, let's see. 2.3. 2.3 is measures of centrality, right? It's the middle. 2.4 was measures of variance, right? How much spread there is, right? And now this one is given a data set, where are you in the data set? That's what you want to see. So it's a matter of position. So let's go. How do you do position? Right here. Don't write all of it, but just the stuff in highlights. What we do is we use something called fractals to figure out position. And fractals are just, you divide the data set into pieces, and then you can kind of see where things are. So the way we divide them is something sometimes called quartiles into 4 pieces. Decimal. Deciles, I think that's the way you pronounce it. 10 pieces, percentiles would be into 100 pieces. I remember, I think any one of you guys taken the SAT test? Did you guys take the SAT test? Okay, some did, some didn't. Okay, that is broken up into percentiles. So like, you got a score of 1380. You are in the 86th percentile, and that's exactly what it is right there. It's the percentile ranking of you compared to the rest of the class. So let's do this. Let's see, time left remaining. Let's jam at least through this piece right here. So we're gonna jam with the first one called quartiles. So quartiles, what are they? Oh, went back a little fast here. So it's approximately dividing the order set into 4 equal parts. So you have Q1. Q1 represents the first quartile, about a quarter of the data. Fall from the beginning to quarter to Q1. Second part, half the data now is there. About half the data falls lower than that. In fact, Q2 is actually the median. So remember, think back to what we did for median. Something about ordering the data and figure out the middle term, stuff like that. Okay, Q3, that means 3/4 of the data falls below that. And then you can kind of tell that everything is kind of quarters based, right? Everything's a quarter based. I think a Canvas, when we take our first test, you guys will go into test results. So when you click on it, it actually does this for you. It gives you a quartile and it tells you where you landed on the quartile. Two. Okay. Okay, talk to me. How we doing? So Q1, Q2, Q3, Q2, just kind of make sure we remember that is the median. And then really, if we think about it, Q1 is actually the median between the lowest data set and the middle. Okay, we're good. Got those people doing it. So let me go through just quickly a few things here. I want to get to one spot here where we'll stop. So, bless you. If we do this here, don't write this down, but just kind of think with me here. I have this data set. What should we do first? It's the each year the U.S. automobile commuters waste fuel due to traffic congestion. This is the amount of fuels wasted by computers in 15 largest urban cities listed. Find the first, second, and third quartiles of the data set. What do you observe? So let's talk about it here. So first things first, we have to order the data. We good? We go from the smallest to the largest. Give me guys the smallest. 11 right there. Boom, 11 goes first. And we go 11, and then we just sort them out. And then how many numbers do we have real quick here? 15. So that means the seventh one will be our, or eighth one. Let's see, 1, 2, 3, 4, 5, 6, 7, eighth, right? The eighth one would be Q2. Remember our median? Median is just chopping off the sides, getting the stuff that's left over. Boom. Then what we do is we chop off some more. Then we say to ourselves, okay, now I'm left with this right here. Let's see how many data points here. 1, 2, 3, 4, 5, 6, 7. So if I chop off 3 here, chop off 3 here, 23 will be Q1. We good? So it's the middle, then it's kind of like the middle of the lower half, then the middle of the upper half. There's our Q3. And that's cool. So then the question is, okay, where's things lining up? How do things work? So 2 things out of this that come out. I want to show you real quickly here. I'm not going to get to what I wanted to get to. So now the question is this. Another question is this. Are there any outliers here? Is there anything that's kind of like really off in the data? And so I'm thinking to myself, you know, at the top end, I see a 30, 33, 35, 35. I like the top end. Looks like everything's kind of is together. We good? Look at the bottom end. Bottom end is 24, 23, 22, 20, and then you got this. Boom, 11 drops off. Now the question is, how do we know that's an outlier or not? We're good. Let's can we keep that in our minds here. But first we do that, one more definition real quickly here. Something called the inner quartile range, the IQR. It's the measure of variation that gives the range of the middle portion. So about half the data falls under here. That's kind of what we're looking at. Half the data falls here. All right, and how do we do this here? The formula for it is IQR. So IQR is Q3 minus Q1. So Q3 minus Q1 is what we do for The inner quartile range, that means 50% of the data is going to fall right here. Okay, and what we do is we kind of say like, that's the main data right here. This is what we do. This is the one that we look at because the majority of the students tested here, or the majority of the population was here. In this case, it was the amount of fuel lost because of just people sitting on the side of the, not on the side, on the highway instead of driving. Okay, let's do this here. A little time left. I'm going to show you the how we do a graph of this stuff. We're good for, and we'll stop there. But then we'll go back and we'll talk about outliers. How do we think about outliers? We are, let's see if we're going to draw a graph of one or the other here. Eventually, we'll draw the graph of the data that we have here. Not today. Yeah, Thursday. Okay, let me show you what this looks like, and tell me if you guys seen this before. Have you guys ever seen something like this before? Where? Tell me where. Previous math classes. Okay. Ever seen it in your Canvas when you look at the test results and you click on details or extra details? It has like this little piece right, and that has your dot where you ended up, where you are compared to the rest of the class. But this is a comparison right here. So if you were to say, hey, your dot is right here, like, hey, wow, I'm about at 75% of the class ish, right? Or here, I'm like, wow, I'm right in the middle of the class. And so we go from there. Okay, let's stop there. Those